Hello. Hello. Am I
Yep.
audible?
Yes, sir.
Yes,
Okay.
yes,
Thank you.
audible.
Okay.
So you are not audible.
Yeah. Okay. Uh, one minute. Uh, okay.
So, sir, are you recording this session? YouTube live?
Yeah, it's already live.
Okay.
Sir, it is
Yes.
not showing on the channel.
It's not showing on the channel.
Just send the link, no, sir. I'm gonna circulate. Thank you, sir.
Yeah, okay. It is. Fine. Okay. So in quiz two, we will have from week 5 to week 8 syllabus. Okay. Give me a minute. Give me a minute.
Sir, the sessions which has been conducted on 38th and 27th, where can we find that link?
When tomorrow? Yesterday?
Oh, yes, yesterday once and also the 30th also there was a class. So that link actually I'm not able to find in the calendar.
No, on 30th.
No, the sessions by teaching assistant, I think. Purva Sharma or something. 29th and 30th.
Uh,
Yes,
okay.
Those were still not updated.
the
Not
calendar. The
okay.
calendar.
Calendar.
No, it's not in calendar. She has shared a link, but still the access is denied.
Uh, so on which
From
day session is there?
So 30th.
actually 29th and 30th there were two sessions. So 29th she has shared a link. 30th she didn't even do that. This is the one which I'm sharing in the chat is the 29th link for the 29th. We couldn't able to access it yet. Yeah, that
Okay.
one.
But it's accessible now.
Yeah, it's accessible now. Yeah, okay.
Okay, any other link? Is there?
No, the 30th
30.
one, I think the link she hasn't shared.
So please share now so that we should not miss. 30th. This is the 29th one, which somebody.
uh, 30th one link. Thirtieth one. Okay. It's not here. Okay, this is. I guess it's not there for 30th. We you this one.
Can you share the link, sir?
Okay. Okay. Shared.
Sir, this link you have shared for the 30th one in the live
Yes.
session.
Yes. Yes.
Sir, also share about the 29th one. Sir.
29th one is already there. This GM. Okay. Maybe I'll just copy. Paste it. Okay. Okay, then we'll start. Okay, so first we'll talk about how confusion matrix is being drawn. I hope most of you know, but still let's get a overview. So this thing also you can have.
Sorry to disturb, sir. We are continuing from which week?
Which week? Uh, okay, this is not any week. I am like, this is not in any week, this confusion matrix and all. But we should cover this thing.
Like we are going to cover which weeks in this session?
Which weeks? Like we will cover ensemble technique later on, week 8, and I guess rest of the things are covered yesterday.
Okay, sir.
Till
Thank
week
you.
7 is covered, so week 8 I will cover today.
Okay, sir.
Okay. Okay, so okay. Okay, so what happens is okay. So okay, so let's say we have y, right? Y is like so first we use class A confusion matrix for classification problem, right? So if it's a classification, then we need to draw this. Why is that? So let's say I have y, which is like, let's say 1 1 1 0 0 1 0 1, something like this. Okay, and my y predicted. So I predicted something, and I got y as like 1 0 0 1 1 1. So 3 and 3 is 3 6, and it's a 0 1. Okay, something like this. So by looking at this, I'm not able to identify how many correct classification I made. So first thing is, whenever you do any machine learning or statistics problem you are trying to solve. So let's say statistical problem is is patient so it's like the is patient having heart disease, patient having heart disease, classification problem. Okay, answer can be yes or no. So whenever you're trying to solve any problem, you always put, like, if somebody has a heart disease, like 1. Okay, 1. And so the point you want to find out, and other as no. So let's say, like, is uh, okay, let's say you want to find out machine failure or something related to machines. Okay, machine failure. Then the class 1 will always be when machine failed, and class 0 will be when it didn't fail, right? I mean, see, this is didn't fail is a positive thing, right? It's good that it didn't fail, but we are saying that it's 0. We are giving that as 0, and this is like it failed, so we're trying to find that. That's why we'll put that as a 1, right? Let's say email, right? Email is there now. uh, so your problem statement will be how it's going to be: is spam or is not spam. Okay. Okay, is spam or is not spam? So these are like two. It's not which question you will ask, this one or this one. If your problem is you want to do something with emails, spam emails, right? You want to make a classification model on spam emails. So which question you will ask, is not spam or is spam?
Is spam.
Is spam, right? So you'll ask this and you'll assign 1 and 0 based on this. If you ask this, that will be opposite, right? 0 and 1. And this is not a good way. This is a good way. You should do this, right? So that's why whenever somebody asks, like in binary classification problem, binary classification, like nobody asks like what is precision of class 0, something like this. What they ask is tell me how much precision you have, something, precision score, okay? Accuracy score. So this all are related to this class 1. I mean this question. So class 1. This all are related to class 1. They are not even interested in class 0, something like this. Though it's a different matter that class 0 are also important, but for our case or for our problem statement, we are more focused on class 1, right? If somebody is having a heart disease, then that is like our problem statement. If somebody is not having heart disease, it's not my we do care about that, but we don't focus more on that. Okay. So that's why we build this confusion matrix. Here, so okay, let's draw confusion matrix. So how sklearn draws confusion matrices? You have like this, right? And so these are like predicted. In sklearn, this is how it's being done, and here like actual. So this one is actual or y true, and these are predicted one. Okay.
Sir, one doubt here.
Yes.
Sir, you have written this machine failure. Suppose yes, machine failure. Is it a machine failure? We say yes. Then we assign 1 to it, and no, we say assign 0 to it. So
yes.
How are you assigning this positive and negative, sir?
No. Positive. It's not positive. It has nothing to do with positive. I was saying that when we see it as like let's say this machine failure, right? Negative means like it's not a good thing to happen. Machine failed, right? We don't usually, you'll see your data will be like 0 0 0 0 0 0 0 in this case. If I take this way, and somewhere you will see 1 somewhere, right? Most of the case it will be 0 because machine fails very few times, right? So that's how I was deciding that I was saying positive in terms of like sentiment. If my sentiment is
Okay,
I don't want my
sir.
machine to fail,
You
right?
have- Okay, sir. Got it.
Yeah, something like this. So it was related to sentiment. It has nothing to do with it. I will just remove. Okay. This also. Okay. So I guess we can do this. So this is predicted one. This is actual, right? Now what we'll do is first see if you see this PPT. It's like we have, let's say we have this kind of data. Then we first classify like what are negatives and what are positives, how many negatives are there, how many positives are there, and out of those negatives, how many were true negatives and how many were false negatives, something like this. So we'll build like this thing, okay, and out of positives, how many were true positives and how many false positives. So in this case, wherever true you are seeing, true negative and true positive, is where machine was able to means model was able to correctly predict. Okay, and wherever falses are there, that's where our model was not able to predict it correctly, right? So that's how we got this number like 1, 3, 2, and 2. So it's like this, like 2 process. So 1, this is like actual, right? We told that it's a class 1 and it's coming out to be class 1. So that's why this is true, positive, and true. And here like negative, and it's
Sir,
true.
actuals are on the left side. Actuals are on
No,
the,
no.
I mean, the
Yeah,
top ones
actuals,
are
yeah,
predicted.
these are actual. So these are true or
Right.
actual.
These are the actuals, and upper ones are predicted.
Predicted, yes.
Okay.
So this is how sklearn plots it. So you will see somewhere in opposite way also, some textbook or somewhere, but this is how sklearn plots it. So that's why I kept like this. Then okay. So this is how we get the confusion matrix, right? After we get the confusion matrix, we have this all questions like what is accuracy, and which accuracy is how much I was able to truly predict out of all of it. So like true positive plus true negative. So true positive, true negative will be on diagonals, right? This one is true negative. This one is true positive. So it's like 3 divided by all of it, right? All. This. Okay, and precision is precision is like how much truly I was able to predict out of all the positives. Like so, okay. So where is true positive and false positive? So if you see, this is like true positive and false positive, right? So this is, if you see this class 1, actual 1, and this is like true positive and divide by all. So like you have to see the predicted ones, right? Out of all the predictions, how much true was there, and in recall, it's like how much you are able to predict from the actual ones. Okay, and so recall goes like this. So you okay. Uh, so this is a recall. If you go sideways. Or horizontal, and if you go vertical, then that is like precision. So that's how, like, it's very easy to remember that a horizontal is precision, true positive divide by or both of them. And in recall case, it's like true positive divide by true positive plus false negatives. Okay, and so this is how you will be able to compute this all. Okay, and there is one thing called F1 score, in which case you take harmonic mean of precision and recall, right? So it goes something like this, like 2 divided by 1 by precision plus 1 by recall, or to simply say it, it's like 2 multiplied by precision recall divided by precision plus recall. And if you compute that, it's going to come out as 4 by 9. Okay. Okay. So if imbalanced class is there,
Sir, could you please show the previous slide?
slide, okay.
Okay, sir, got this F1 score.
Okay. It's a harmonic mean of precision and recall. Okay. Okay. So so let's say this was earlier, like it was kind of, I would say, balanced. Labels were balanced, but what if they are imbalanced, like they are not balanced, right? So you can see we have too much true negatives. So 990, like let's say, is fraud, right? Something like this. So fraud is maybe credit card fraud or some other kind of fraud. You can say credit card fraud. And if this is the case, then fraud happens rarely, right? Not with much more people. So most of them are 0, and our model was able to predict that there is no fraud, that's good. The problem lies here, right? We even like we want to find out with whom the fraud is happening, something like that. So in this case, if I try to compute this prediction 1 star 7, true zeros. Give me a minute. Okay. Yeah. So I think I wrote is predicted is like how many predicted zeros. So prediction goes like this. So 990 plus 2. So 992 is of that. And class 1 were predicted 8, right? So should like okay, if okay, can't add it from here. Maybe I can. Okay. Okay. So class zeros were like 992 and class 1 in prediction case. So prediction is like you have to see vertically, and 992 were class 0 and 8 were class 1. Okay. I can have. And in true cases, if you see, so 993 were class 0. Okay. And if I see class 1, they were 7, right? 5 plus 2, 7. And if I try to compute accuracy, it's going to come out like this much, right? It's very huge accuracy. So 995 out of 1000 is like 0.995, right? Zero 0.995, something like this. You'll get this much accuracy. Though our model is doing good job or not, we can't figure out using this accuracy. If we have imbalance classes, then we can't rely on accuracy, right? I will write it here. We can't rely on this. And if I see a recall, that is like 5 by 7. That is okay. I mean 5 by 7, 5 by 8. But if there is imbalance classes are in there, what we usually do is we usually use this F1 score. Like it's best suited when we have like imbalance classes, right? So like okay, this is only computation. Like whatever I did it earlier. Like this is the formula I use to compute this all. Okay, so like if you have imbalance classes, then use F1 score as a scoring tool, like scoring evaluation metric. Don't use accuracy or precision or recall also. So sometimes it works, sometimes it doesn't work, like recall and all. But with F1, you are certain that it's like good for this one, like imbalance classes. Okay. And
So, sir, what is the maximum F1 score is possible?
1. Maximum is also 1. F1 score. Okay. So okay, so usually we have like binary classes, right? 0 and 1. So like 2 classes. So in this case, what we do is we take precision as precision number. Okay. Okay. Yeah. So if you take like macro average in this, so I'll show you. Like I'll open the collab. Here in this I can share.
Sir, would you be discussing some previous year question paper today also?
We can do that. We'll
Sir,
see.
in April 23 paper, there was
Okay.
a question on this one, recall and F1 score. So
Okay.
they have given all the three as answers. It was an imbalanced status.
Yeah. So we changed that later on. Like only recall was the right answer. Yes.
F1 score. No?
Yes, only F1 score.
Okay, sir. Thank you.
Let's say I have X as, or not X, Y as
So, sir, why F1 score not a correct answer? Why not a recall or precision?
because okay. See, in precision, okay, it's not here. So in precision, what happens is you have true positive plus false positives,
Mm-hmm.
right? So it's like here, right here, something like 3, 2, and out of this we need to find out. And if it's an imbalanced class, then whatever precision I'm getting is not as how would I say, is a good metric in this sense, because we will have higher precision itself, higher accuracy you will get. Precision is also possible. It's possible that you will get higher precision. Okay, so let's say if you have too much of class 1, like too much means too many class 1 are there, like 900 or so, and if you try to compute this precision, then you will get 900 out of like whatever the like class 1 were there predicted were true. But in reality, it was an imbalance case, right? We have too much data of class 1, and we are able to predict it as a class 1. So it's not a, we can't say anything about model itself, right? If your model didn't do anything, we are not sure that it didn't do anything, right? It's like,
No, so my specific question is, suppose I created, I am detecting cancers. Okay. Now
yes,
in the cancer says I am creating more false negative cases.
yes.
Okay. Then recall will be a much more better matrix than a F1 score. Because if you have a situation, sir, that if it is a false negative, that means people have a cancer, but they are not able to detect it.
That is true when we want to reduce the negative how would I say, false negatives, right? That is true when you want to reduce false negative. That time we use recall, because recall will tell you how much false negative you have, and then you can reduce that. But the thing is, with cancer data set, it's not true. You will not get that kind of cancer data set that out of this many patients, only 2 were cancer patients or something like this.
Mhm.
Because if you collect that kind of data and try to build a model, then it's like you are doing sampling bias itself. So that's why, like, even statistics will say that don't do it. Before you go to the machine learning, your statistics itself will say that don't make model on this. Go and collect better data, something like that. So that's why you should not do that on that kind of data. But if it's an imbalanced case, like credit card fraud or some other thing, in which case you can't able to get better data, like this is the data you will get every time you sample, whenever you do. In that cases, like recall and precision and accuracy are not a good scoring tools. That time we should use F1 score.
Okay.
Okay. Let's say I have y true or let y true. It's like seven. So is right? Yes. Okay. No, and this. And if I create a Y prediction, let's say I have zeros, and how many were in prediction? Like true 993 and 7. Prediction is 992 and 8. Okay, let's plus star 8. I think prediction is 992 and 2. Okay, this is the. So these are like 2 arrays I created, so we can compute precision recall on this. Okay. Okay. So let's say from sklearn dot metrics, I import precision score. Precision score, recall score, accuracy score, and F1 also. Okay. So always what we do is we first write y true. In most of the cases when we do, we write y train. Okay, y train, and this is like y predicted. And okay, what is it? This is okay. I got precision of this much, right? If I draw confusion matrix, display dot Okay. From predictions, y 2, comma y prediction. So this is how we get the data. So these are predicted labels, okay, 0 and 1, and these are like true labels. And how much precision I have is 7 by 8, right? It's like, right, it's like 7 by 8. This is the precision score I have. And yeah, and one more thing is, the first thing which I said is, we usually take which are our problem cases, right? Our problem is credit card fraud. So whenever fraud is happening, so it's a 8 time fraud happened. True, right? True means 8 time fraud happened. In this 7 time, it was able to predict, because we made it like this. We can even reduce it also. So let's say predictions were like, we were able to predict like 3 times only out of this, and like 997 times we couldn't able to, right? Three. Oh, understood. It's the way the array was being designed. That's why this is coming out like this. We can do this. Maybe let's say 4 here. And 4 here. So now you see the precision is coming out to be, so out of 8, 4 times I was able to predict, and 4 times I couldn't. So that's why I got precision of 4 by 8, right? 4 by 8, something like this I got. And is it a like good one or bad one? I can't say in this case, because this is like imbalanced data set. Usually I should not rely on this method like precision score here, because the classes were imbalanced. If I use like recall score, that is also like kind of coming out to be 0.5. Accuracy will get high, certainly. Okay, so this is like 3 out of 7. Class 1, right? 3 out of, no, 4 out of 7. And accuracy is 993%. So like, was it a good one? Because our precision, or from the confusion metrics, I'm able to see that wherever the important point is, like I wanted to find out when the fraud happens, in that it was able to find out 50% of time, not better than it. But our model is saying it has very high, good accuracy. Though I should not judge. That's why we should not judge on accuracy and precision recall itself. So that's why this F1 score we have, this we can use.
Okay, you mean that F1 score is a mix of precision?
Yes.
We use both of these rather than relying on them individually.
Yes, individually.
So it is better to use F1 score because the classes are imbalanced.
Correct.
Sir, could you explain the above, like how did make difference from y underscore predict as 1 into 4 plus 1 into 4 instead of 1 multiplied by 8, like above array, y underscore predict. Y underscore predict, yeah.
Y underscore predict, how I wrote this? What is it?
Like what made the difference as 1 times 8 and splitting it into 4 and 4?
Okay, so it is like, you'll see it gives you an array. What I wrote is just array, nothing else, right? So it will start from 1. So currently it's starting from, okay, see, it start from 1. So I wrote 4 1, like that's what it says. Then I'm adding zeros into it, 992 times, and then I'm adding 4 like this, right? So
Yes, sir. But here, like before you wrote one with times 8, like there are 8 ones at once. Now you split it into 4
okay,
and
okay,
4. So,
okay. I'll explain this. So let's say if I write 2 2, and let's say I'm taking 3, this one, right?
yes, sir.
If you see, this is how the array is being made, okay? And if I just write this as this, like 1 times 4, right? Then the array will be like this. Now, can you see the difference? So this is like I'm saying that this is are my predicted classes in these cases. Like it's not a real model, right? We didn't build any model or anything. So I'm just assuming, I'm just randomly taking things uh, here, right? That these are classes I got out of a model like this.
Okay. Like instead, the classes are like perfectly divided, like each half. So, whereas in the
Yeah.
first one, it's more of a different model. We can't predict when the class is ending or when the other class is being.
Yes, yes. So these are like manually given by me, right? That this is how much I predicted, this how I predicted this one, and this is like the true cases were.
Okay, okay.
I can take randoms also, like np dot random, and then like np dot random dot, let's say 0, 2, and I want like 1000, then plus np is not defined. So I will get this kind of array, right? And if I do, let's say if I call this as y train, okay, and then let's say I predicted something, like predicted, and this will give you another array, like randomly some other numbers will be assigned to it. And if I compute something like recall, precision, or anything, so let me just compute accuracy. Though why I didn't do it is because then in this case I'm not sure that it's going to be imbalanced or not. I don't know. Okay. I predicted here it's y train. Right. So it's like 0.502 I'm getting. Or you can even plot this also for this. See, these are just random numbers. Don't get confused with that. I made it so we can understand how imbalanced classes are there, like how we can utilize, what should we do in imbalanced classes, like so predicted.
Well, we need to like for imbalanced cases, we need to like find the best measure which can be used. So is that the final conclusion? Like we
Yes,
just
yes,
want to find okay, which score will be the best one for that.
yes. So if you have any imbalance kind of problem, then you should use F1 score.
Okay. Sir, could you also share the Google slides of the pre-processing that you have?
Yeah.
Thank you.
Okay. What else we have? So we were here. Okay. Let me- Okay, so this is how I got precision recall, F1 score, and all, which we earlier did it like same way. Okay, and I got accuracy of 0.993. Okay, 0.993, and if you see F1 score for, so here you will see F1 score for both of the, so like this is a class 0, you are getting all of the precision recall, F1 score, and support. support is just how many were class 0 and how many were class 1, like counts of it. Okay, and you are getting for class 1, but if you use any like this recall score, how much is precision score, then it gives you for class 1 only, not the average of both or anything. It's just for class 1, because like we discussed earlier, that by default we should always think about class 1s, the important point we want to classify, right? The task of our problem. Then okay, so what is this macro average and weighted average? I will explain that. Okay, so when you take macro average, then it will take precision of class 0, then precision of class 1, and divide by number of classes. So in this case it's 2, but it's possible that you have more classes of 0, 1, 2, 3, then all the precisions divide by number of classes, right? And recall is same thing, like average of both the things. So if you take macro average, it's going to be just the mean of it. You can say mean, right? And if it's a weighted, then so what we are waiting on? So how we are giving the weights here is we are taking precision, okay, and how much actual zeros were also there. So in this case, like actual zeros were 990. So this is like imbalanced case, but still, like for this example, if I say, then whatever precision of class 0 was there, okay, multiply by actual zeros, okay, actual zeros, and then actual ones. So actual zeros were like, how many actual zeros are there? Like these are actual zeros, 993, right? These are actual zeros, and these are actual ones. So 7 were actual ones, right? And this are P0 and P1. P are, I'm denoting as precision for class, each classes, divide by total sample. So this is how we will compute this weighted average and all. So if you see here, right? So if you want to compute for, let's say, macro average precision is going to be just the mean of it, right? So mean is like 1 plus 0.5. I'm taking this two. Okay, I'm taking so for precision, I'm taking this 1 and 0.5, right? And mean of that is going to be divided by 2. Right? So this is macro average, and weighted average is going to be, so this 1 time 993, 1 time 993 plus 0.5 times 7, right? 0.5 times 7, and I should divide all of this by total number of samples I have. It's not 100, it's 1000. So this is how I got this weighted average. So 0.99, like 65 was truncated, but it's the same thing. This is how we will get weighted averages and all. So let's say if I have like y true, is equal to, let's say, class 0 times 2 plus class 1 times 3.
Sir, could you please scroll a little bit up? A little bit, so that precision, recall, and okay, enough, sir.
Okay, class 2 times 2 plus 3, let's say 5. Okay, so let's say if I have this 2, okay, I can show you what it is. Where I missed 2 times, okay, should be this. Okay. And if I write y-pred, can you now compute this thing for like precision recall or anything like weighted? Can you compute this weighted precision score? I can plot confusion matrix also. So okay, so we have this thing, and how we compute the precision? We take, so if it's going to be class 0 precision, then we take this true one, right? True, in this case negative, and then divide by the rest of this 2, right? 2 plus 0. Then if it's class 1, then 1 divided by 2. And for class 2, the precision is going to be 4 divided by 4. Right? So something like this. But we'll come to that later. Okay. So let's say if I want to compute precision for class 0 is, it's going to be 2 by 4, right? And P1 is going to be 1 by 2, and P2 is going to be 4 by 4, right? Precision for class 2. So you have to see the columns, right? Columns you have to see vertical columns you have to see, and wherever like both. So this is like class 0, right? Class 0, and wherever class 0 is true, I took that and sum of the columns, right? How many were there? That's how I was able to find P0, P1, and all. And if I want to, let's say, compute weighted precision, then what I will do is I'll take precision P0, which is like 0.5 in this case, 0.5, and star. How many were 0? Actual zeros. So 2 were actual zeros, right? I'll take 2 plus it was like again 0.5 star. How many were class 1? 3. And then if I take another one for class 2, it's going to be 4. No, 5. 1 time 5, right? And all of it should be divided by totals. So the total are 2 plus 3, 5 plus 5, 10. So this is weighted precision, right? Zero 0.75. So you can see 0.5, 0.5, 1, and this is weighted average precision, 0.75. Right? So this is how you should compute weighted one. And for macro average, you have to take the mean of it. That's all. Like so, mean of this 0.5, 0.5, and it's a 2 by 3, right? 2 by 3 is the macro average precision, 0.66. So here they truncated to 6.7. Okay, same thing. So can you compute for recall, like, or we can give a minute. I'll just change a bit. Maybe let's say I will do so 3 and 2. Okay. So if I have this confusion matrix, can you give me average recall? So this weighted average recall, this one. This is not the this, right? Precision recall, correct one. You have to compute from this precision recall. Can you tell me that? Can you compute it? I'll give you some time, 2-3 minutes. You can wait.
So like precision for what, which label?
Okay.
Because it is not only positive and negative.
Weighted average. Weighted average recall for class 1. Okay. You have to compute this.
And sir, in scenario of this multi-level, if we
Yes.
do only precision, if we call for only precision score,
Yes.
then for which class does it predict?
For this, you actually you can't. It will throw an error.
Okay.
But in this, you have to use something. So, see if you do this. So okay, we will come to that. It will throw an error. How to? So we can take weighted average recall or precision. We can do that. Okay. But can you do this thing like weighted average recall for class 1? Can you compute that?
It is 1/3, I think.
Okay. 1.1. No, it can't be 1.3. Wait.
1/3. 1 divided by 3.
Okay, 1/3. Okay. So 0.33. Okay. Anyone else? So it's the same way. Like this is the way you have to compute. Okay. Like you're able to solve it or not? I don't know. But let's see. Okay. No, it's coming out to be 0.5. So this is incorrect. Okay. I drew this correct only. And now we can take classification.
Sir, you are not audible.
So screen is jammed.
Sir, in the earlier confusion matrix, you have written in line number 47 that 2/3. How has this arrived? You have arrived at this 2/3.
Hello. Sorry, I lost connection. I'll share it. Hello. Am I audible?
Yes,
Yes,
sir. You
sir.
are.
Okay. So somebody gave 0.33, but it's incorrect. Like you have to. Hey, wait. I mean, there is no. Okay, sorry. My question was also. Even though I was also thinking that when you get average recall, when you compute this average, weighted average recall or anything, it's not for anything. It's for the whole thing. It's not for any class. Okay. That. And so if you compute recall for first one, okay. Okay. So if you compute recall for class 0, like R0. Okay. So R0 is going to be
0.67.
2 by 3, right? Yeah, 0.6 R. Then R1 is going to be
1 by 3.
1 by 3, right? 0.33. Then for 2, R2 is going to be
0.5.
R2 is going to be 2 by
4.
4. Okay, 0.
0.5. Yeah.
0.5. Now, if you want to compute weighted, then how much? But that's so 3 times R0 plus 3 times R1 plus 4 times 0.5 for R R2. And this whole thing we should divide by total number of samples. So in this case we have 10. Okay, 0.5. Okay, this is how we should get. So okay, I think it's good enough. We can move ahead. That's okay. That's it. Okay. Now another point is okay. This is another slide in which like so how to
Ravindra,
how
can you please mute?
okay. One of the important task we have to do when we have text data is we need to extract the features out of it. So the text can be anything like paragraph, or in terms of sometime it is like given in small sentences also is possible, right? And generally like what we have is like we call that as a corpus, like multiple uh, multiple multiple sentences are there, and multiple paragraphs are there. We call that as a corpus, and we want to take out the features out of it. So to get the features out of them, we have this techniques. Like one thing we can do is we can just count which words are there. Like words means this tokenizing is a word, string is a word, and is a word, giving is a word. So we just n integer, we just take all the words out of it, we create feature of that, and then how many times it is repeating. So let's say in the first paragraph it's repeating like 20 times, then we write 20 there, count. Then in second paragraph, like maybe 25 that we write. So that's how the feature will get built, right? The column will be like this. So if I, let's say I had, so my row, if I write row and like columns is there, right? Then for 0, I will have count, right? 20 words were repeating, and the column name can be like this. Okay, this is like this is a column name you'll get. I'll show you how using vectorizer itself that you'll get this all. Okay, and then 20 in first row or first paragraph, and then 10 in second one, let's say, and then in this possible, it's possible that you might not get anything also, and in 3 you'll have 15 or something like this. So this is how this features are being generated, like feature extraction. We call this as feature extraction. Then another feature can be anything, like in same paragraph another word whichever is there, like example apple, book is a word given in that. How many time book is repeating, count of that is possible, like 2, then maybe 3, then maybe 4, and like 0 here, it's not repeating itself, so something like this. So this is how we build the feature. We call this as feature extraction, and this is an important part if you have text data. And counting is very easy, right? So this is very simple. Just count the number of time a word is repeating and give that's all. So if I write sklearn dot feature extraction import feature extraction dot text type, right? Count vectorizer. Okay. So I'll just create something out of it. Okay. Okay. Okay, so let's say, okay, I'll just take this feature dot transform, get features name out, and just copy this, and here is this corpus. Okay, count vectorizer. I don't want this. Okay, so this is like corpus, right? So this is like first sentence, then second sentence, third sentence. It's possible that you have more than sentence, like paragraph is also possible. Okay, here we have sentences, but paragraph is also possible. So this is like first document, right? We generally see this as a document because we whatever we extract from one document, we want to keep it together. That's why it's there, right? One document, then this is like from second document and third and on, so on, right? Now what we have to do is Okay, we have to write this one. If I do this, it will learn all of it. Okay, I'm getting it. So fit transform, this is giving me some compress sparse. Okay, I can do array. I'll get this. Okay, CS. Okay, so this is the counts I got, and which count is what I can do that also. So if I write, let's say pd dot data frame, and this is my array, and if my columns I want, then I'll write get features name out as columns. I'll use this as columns. Okay, so you can see, so this is my first document. There is no end present in that. Is document present? Yes, once it's present. And first present? Yes, once it is present. Is one, or everything is once present. Okay, in this 2 is there, so end is not present. Document is present twice. This document, and here again it's repeating itself, right? This document and this here also document as well. And the way this all features are all in ascending order, right? So end is like starting from A, then D is after A, right? Something. So this is how the columns are named, and it's giving you count like that. So this is how
Actually, I have a question.
Yes.
It won't include the full stop and other punctuation points, punctuation marks. This is
why
the first.
this? Okay, so there is one parameter is for that, which didn't let it to add this full stop and all. It will remove it. Comma, full stop, and some other kind of thing will get removed. Okay, so let's say if I have comma also, it will not be counted. Yes. Okay. So and okay, in this stop words, several known issues with English, and you should consider an alternate. I guess that one was there. Analyzer. Ability. Yeah, this one only. Okay. The stop words are there. Okay. In this, the list is already given. For English, it's there. The using stop words. Okay. Stop words are word like and, the, him, which are presumed to be uninformative in representing the content of a text, and which may be removed to avoid them being construed as signal for prediction. Sometimes, however, similar words are useful for prediction, such as classifying, writing style, and all. So like in stop words, it's given by default for this count vectorizer that don't take dot, comma, and all. Okay, so that's why these words are not being counted. So like in this case, our like end is getting counted. Okay, end is getting counted, but what they wrote is like in stop words, it's there. You can put this in. Okay, it's a callable also. So what I mean by you can give list also. So so let's say where was vectorizer? Yeah, here. You can write something like stop words. You can give list also, like don't take comma, Don't take and don't take which one I want is. Okay,
Is
that's it. Okay, so everything will be first like being converted to lowercase. Okay, so
okay.
if you write like the and the, both are same, it's not going to change.
Okay. Okay. Okay.
So it's going to convert into lowercase. So you can write everything in lowercase. That's fine. And now if I do, then I have this only. Okay. So document first, 1 second, the third, and
Yes. And is removed. Yes.
this and is removed, and I give comma also, which is here. The is here, so it's saying once it's present, and okay. So I have to see like, so this is how you should write stop words, and in this like so in this like case, comma is not getting counted due to some reason, like in counter somewhere else is also there, some other parameter is also there, which is not letting it counted. Okay, like in maybe token pattern or something, right? In this like few parameters are there which are helpful, like one is this n-gram. Okay, you can give, so currently what's happening is it's taking words as a count. You can take n-gram also. So by default it's 1 by 1. If I write 1 by 2 or 2 by 2 or something like that, then that means it will merge two words and then give you like new features, like this is also is going to be feature, like is also going to be feature, the first is also going to feature, something like this. So if two words
Excuse me, sir.
together, then we can do this way.
Sir, could you please share the collab file as well?
Definitely. See,
Sir,
like
I am not getting this n-gram range.
What is this? Okay, so without n-gram range, what happened is, so see, without n-gram range, I'm getting only the single words only, right? Just the words. One thing. If I change this n-gram range, so currently n-gram range is 1 by 1. Okay, I can do 1 by 2 also, or 1 comma 2. If I do this, it will give me like it will take two words at a time. So now I'm taking one word at a time as a count, but this will take two words at a time. So this is like two words at a time, and this is also two word at a time, two word at a time, something like this. So if you want to do like this, then you should write 1 comma 2, and you'll have something like this. So here you can see this was like earlier this much we had, right? Document first.
Sir, this means that it will treat two words as the same unit, right?
Two word as a
single unit. Like third
yes,
one,
single unit,
again, it will count it as one.
Yes.
Again, the third one is it encounters third one, then it counts as one.
Yes. So let's say some words are there in your documentation which were making sense together, like
Yeah, like together or in between or just together.
Yeah, something which are making sense when they are merged, then they make sense. Then that time you should use this n-gram range to create a
Now I got
column.
it. got it.
You can change it to something else also.
Sir, so it is working like polynomial features, we can say. It is creating new features without interaction.
You can say that, but in n-gram range, yes, it's the same as polynomial features. But in polynomial feature, what we do is we multiply them. Here we are not multiplying them. Okay, we take multiply, we take power of that feature, and like that, right?
And
so
sir, what?
we are not doing that.
Okay. So what will happen if we put, yeah, the same 2, 2? So 2 words for 2 words. So it should have no effect, right?
No, it's like only 2 words we are taking. Only 2, right? See, only 2. This is 2 by 2, 2. Now the one word were removed. Only we are getting
Okay,
two.
okay.
Only, right?
Okay, so it started with directly 2 words. Okay.
Yes, it started directly 2 words.
Okay, okay, got it. Thank you, sir.
Okay. And is there any other important? So this max DF, minimum DF is the count. Like this much count should be present. Okay. Simply walk away, ignore terms that have a document frequency strictly higher than the given threshold. Okay. So let's say something is repeating too much, like the is repeating 100 times, and if you write something is repeating more than 20, remove that. Okay. You don't want to. So the is will repeat many more time, right? So you can directly remove that feature itself by giving some range in this max DF. Okay. And minimum DF is also like some words are there which are least repeating. You can remove that using min DF. Okay, either mapping a dictionary and keys and terms, vocabulary, have a gap between 0 trebles. Okay. Example, a dictionary. I'll explain that also. Dot vocabulary. See, I'm getting this the 8, 3, right? You can give this also as input also. Like I'm not sure where it is useful, but you can give it as input, like the small version of it. Like you can write in this way and give it to it, right? So let's say I don't have n-gram here, and so I'm removing this also. I'll just keep it. Now I'll remove this. And if I run this thing, now vectorize a dot vocabulary. Okay, so see, I can write this dictionary by hand also. Okay, by like I can decide this dictionary and give as an input also. That's what this vocabulary parameter is saying. But though I don't know why it's let's see. I will give vocabulary or do okay. Oh, what I'm getting. Contains repeated indices. First. Oh, okay. I kind of did it. Something like this. 2, 3, 4, 6, 7, and 8. Okay. Okay. So see earlier. Earlier, what was happening is I'm getting this vocabulary in a certain way, right? In a ascending order or something. If you want in any other order, you can just give indices like this. So if I want, let's say this as a one index or anything, like say I want it as a fifth index, then I can do that. It's just I'm getting vocabulary in different indices, like columns will be in some other way. That's all. Okay. Okay, I hope this is. Now we can now move on to this one. So this was vectorizer. Now, okay, so I'll just explain this TF idea. TF idea is being computed using two things: term frequency and inverse document frequency. Okay. It's not. Okay, I'll try to explain in this. And I can't go out. Okay, I'll use this and explain. So in these two terms are the TF idea. One thing is term frequency and inverse document frequency. So in term frequency, what we did earlier, like just counting, like numbers, right? So if you see TF, term frequency is how many times word appeared divided by total number of words. Like when this vector is there, term frequency. So this is present in this, like, okay, so this is an example, this is a sample, and this is another example. So this is like two words. Let me take it to collab, and then I can just write it here and I'll explain. Okay. So first thing is like term frequency, right? Frequency is usually, see, in physics, if you go like, don't get confused, but it's always like 1 by time. Okay, this is what we call as a frequency. In this case, it's going to be count divided by total words. Okay, something like this. So count divided by total word is going to be TF. It's very easy. So let's say I have word like my country is India. India is beautiful. Something like this, right? So if I this is one sentence, okay? This one row. There's not two rows. Second row can be anything like India is something self-reliant. Okay, something. So this is my second row. So this is like row 1 and row 2. Okay. So if I tell you what is the term frequency of India, TF of India, in row 1, it's going to be how much? 2. So
2
2
by
times
7.
right? 2 times it's repeating. So don't worry about the
2 by
upper cases.
7.
Okay. That is fine. So we always convert that is everything into lowercase. So 2 divided by 1, 2, 3, 4, 5, 6, 7. 2 divided by 7. Okay. And then in another one, like the second one, it's going to be 1 by 4. Okay. So this is how term frequency are computed. This is called term frequency. Then we have inverse IDF, like IDF. It's called inverse document frequency. Okay. And that is being computed like this. So this is the formula, like logarithm of something. I can and put this also. So it's something like this, like log of 1 plus n divided by 1 plus this DFT. So this DFT is, I guess, that is term frequency. Okay, the count rows in which word was present. Okay, number of rows. So number of rows we have is 2, n is 2. And count in which the word was present. Okay, so in how many the word was present. Okay, so DF, like document frequency. You can say this is document frequency. Okay, I'll write this as a document frequency. So in how many document it was present, that we can write here. So it can be present in all, like 2 it's possible. It can be present in 1, or it can be present in none, like both of them, right? Something like this. So this is like document frequency. And so this example is given. Now what we have to do is we have to multiply term frequency. We know how to compute, and we know how to compute IDF also. We will multiply both of this, and this is called TF IDF. Okay, this is how TF IDF vectorizer works. So let's say
Sir,
yes.
One doubt here. Document frequency is what you have mentioned here, and IDF is the inverse of this.
Inverse document frequency, yes. Not inverse of this. No. See, term frequency is, see, term is just the word. Okay, word frequency, you can say. Just
Yes,
the
sir.
word. Just the word. But inverse document frequency is, in first you will see in which document the term is present. Okay, it should be present there, or it's okay. So it's okay, it's not present. If it's not present there, we can just give 0 to that. Okay, and so this is a related
could you
to
please?
document. Sorry, go ahead.
Sir, I am not getting this inverse document frequency.
That's fine. That's fine. See, we'll compute how IDF is being calculated. You'll know how to do that. Okay. So let's say IDF is there. Okay. What I have to do is I have to take log. Okay. 1 plus what is n? This is the function of IDF. Okay. This is how we compute IDF. Can you see this? So this is how we compute IDF. Okay. So let's say I want to compute an IDF for term. Term is, let's say India. India is the term. Okay. I want to compute this for India. I will take log. Okay. I will take log 1 plus n. What is n? N is n is number of rows. So in this case we have 2. Okay, that is okay. We know it's this. So the total is 3. Now other point is DF. This DF is like count or rows in which the word was present. So in this case it was present in both of them. So this is also going to be 1 plus 2. Okay, 1 plus 2. And then the whole thing, the logarithm, whatever comes up, we will add 1 to it. Okay, we'll add 1 to it. So after this logarithm, now let's say I want to compute IDF for something which is not present in both. We take something. Okay, so this is row 1. My country is India. Okay, country is not present in both the case, right? So I want to compute IDF for country. It's going to be log of 1 plus n. N is number of rows. It's still the same, right? Number of rows are not going to change. What's going to change? Now, what is DFT? Count rows in which the word was present. Okay, in which so how many times it was present? Once only, right? So I will write 1 plus 1. Then this one. Okay, so this is how you will compute idea. Can you able to understand?
Yes, sir. Now I got it.
So you have to remember this function of IDF. Like this is how IDF is being computed. Okay.
So, sir, where I use this TIDF and counter vectorizer? Means in which case I use this?
Okay, see, in this what we are doing is when words are repeating more or something like this, right? We are so in that it's simple, like just count of it, right? 9, 10, 11, 12, anything. In this, it's like inverse of it. So if it's present in more documents or something, then we can kind of ignore that feature. Let's say if it's present in all of it, right? All of the documents, the word is present itself, then it's not going to change anything, something like that. You can think of that way. And sometimes, though, it's important that that word should, if that word is present in everything, then we can focus on that. That time also we can use this TF-IDF. Okay. By this, you will know that in how many documents the word is present.
So the calculation here will be 1.17, is it? For country?
For this one?
For country.
For country, yeah. So you have to take log of, you can take like NP dot, maybe
3 by 2. So that is log of 1.5 plus 1.
1.5. Yes, and plus 1. Or wait. Yes, you have to take this. Okay. In this, I did TF is this, and IDF is log 3 by 3 0. Sorry, log 1 of is 0. Okay, yeah. So this is how you get IDF, and TF multiplied by IDF is going to be, so let's say for country, the term frequency is present in count is 1. What happened to this one?
Sir, in exam, do they ask us to calculate this term frequency or inverse term frequency?
Yeah, it's possible. Like we can. So this is how this thing is computed, right? Somebody was asking me. That's why I am doing it. We can actually. So it's just like this completed. Like this is how you computed TF-IDF. Okay, this is it. It's here. Okay, how this thing is happening? Somebody asked me, so that's why I prepared this and I'm showing it to you. This is another example. Like this, these are 2 rows, and you compute TF term frequency, then IDF you compute, then you multiply that term frequency with IDF, and you get this values. This is how the TF-IDF gives you the feature extraction. After feature extraction, you will get this values in the features.
So, sir, here we take the natural logarithm, right?
Sorry?
Not the log. We take the natural log here, right? Not the log.
Yes, log E base, correct. Log E base you get.
Sir, kindly share the link of this collab.
One doubt, this TF is only for the one document or it total term frequency?
Term frequency we have to compute for all the
document or
yes,
only one row?
Yes, all the documents. Term frequency is going to be different. It's inside the term, inside the document itself. That's why. but IDF is going to be one value only for all the documents. We'll get one IDF, but TF will get for every document. Okay, so TF1 you'll get, TF2 you will get like TF3.
But you're doing TF into IDF, no? So that's what.
Yes.
What
And
is that
IDF
TF?
IDF is going to be constant for each.
Yeah.
For a word. Okay, so let's say the word is country. Okay, so for country IDF is going to be constant, but for TF1 country can be different and something like this.
So the question will be depending on the first document, like that. How will it be? Because the
Depending
TF
on
varies, right? You have written as TF.
the TF varies.
So is it total like that? No, right?
No, TF is count. So
No.
So how
I'm
many
asking
times?
about the formula. You written TF into IDF. So which
Yes.
TF you will put? I'm asking, or is it total
Yes.
or particular TF?
Yes. So let's say this is row 1.
Okay.
Okay, so you will take a TF1 multiply IDF, then you have row 2.
That's more. Yeah. For every it differs,
TF,
right?
Okay. IDF like this. Okay. Okay. I hope this is over. Now we can go to ensemble techniques. We can cover that. Okay.
Sir, you have not shared the link, sir. Kindly share it.
I was sharing it. Yes. Okay. Okay, fine. Okay. Now we can go to ensembles. Okay. See, in ensemble we have two things. Okay, in ensemble we have like first thing is bagging and another is boosting. Okay. One more thing is there. This we call as stacking. So in bagging, what happens is we create multiple models. So like M1, M2, M3, like this. So it's like multiple models will be there. If it's a classification problem, we'll take vote of it. Right? So voting will happen. And if it's a regression problem, then we'll take mean of it. Okay, mean. So whatever. So let's say it's a classification problem. It printed 0, 1, 1. Then voting says that the output should be 1. Okay. If it's going to be regression kind of problem, then output would be like 0, 170, 171, 172. and we'll take the mean of it. So in this case, it's going to be 171, right? So this is how bagging happens. Okay. In bagging, one thing happens is what we call that bootstrapping. Okay. Bootstrapping happens. So we build models M1, M2, M3, but we don't give the whole feature matrix to it. So maybe let's say I can give. So let's say I have the total feature matrix of maybe I have 10,000 rows and let's say 13 rows. Okay, 13 columns. So this is how I have. I can give like maybe 2,000 here and 6 columns. Here I can give 5,008. Here I can give 8,003. Something like that. So rows and columns will be different in this, and they are not going to be in sequence also. So maybe it's possible that you will get in this 2,000 you will get first 200 rows, then some in between 300 rows, then again in between somewhere, and like that the total will be 2,000, right? So the rows is also not going to be sequential, like it's going to be out of anywhere in the data set. So this is how the bootstrapping works. And in this bootstrapping, some rows will be there. Okay, some rows will be there which will never get selected. It happens, like it's possibility, right? Possibility. I'm not saying it happens every time, but most of the time it happens. Okay, and most of the time it also happens also. And this whichever rows which were never get selected, we call them out of bag. We call them out of bag. Now, this is
how this bootstrapping helps, sir?
How this bootstrapping helps?
Yes.
Okay, so
like what?
Yeah. So okay, so when we in bagging we build models, right? We want multiple models to be there. So okay, so what happens in decision trees? Let's say I'm taking decision tree. Okay, bagging can happen with any algorithm. Like bagging, you can use KNN, SVM, or SVC, right? If it's a classification problem, okay, and let me take SVM, or what else we have? Maybe linear regression, logistic regression, right? So it can use anything in bagging, but and there is one special case of bagging is random forest. So random forest is a special case of bagging in which I can only take decision trees. Let me write DT. So decision trees, random forest. This is a special case of bagging, in which decision trees are there. Okay. So why bootstrapping helps is if I just take all the data, right? All the data if I take, let's say let me take the random forest case only, and then maybe it is like will explain itself how why bagging is. Let's say if I take multiple decision trees, like this is D1, this is D2, this is D3. These are fully grown trees, okay? And I'm taking the whole data set, like the whole. Here also same thing, and here also same thing. Is there any like difference going to be there in this three? Any difference going to be there? No, right? It's the same thing, right? So D1 is, I would say this all are very similar, very similar. It's going to be similar, very similar. There's nothing going to be different in this. And let's say this one will give 1, this also will give 1, and this also give 1. If I take voting, anything I will have 1 only. What I did is I did made a mistake here. I repeated the mistake twice, even 2 times more, right? Whatever my mistake was here, I couldn't able to correct it, even though I did same thing twice, right? So there is no point doing this, right? There is no, I couldn't able to correct it. So there is no point doing this. So instead, what we can do is We'll create different kind of decision trees. So let's say D1, D2, and D3 are there. Now these are different kinds. How to make different kind? We can supply less data, right? We will not introduce all of the data. So I'll give partial data here, like part of data, maybe some part of it, okay? Part 1, part 2, something like this. And I'll just randomly assign it, like random. It's going to be random. It's possible that sometimes this also happens that same row goes like 3 times 0, the same row. So same row is sample, right? We call it sample also. So that's how we'll create the 3 decision trees. Now there is a possibility that this will show you 1 for a sample, and this can show you 0 for that sample, and this can show you anything 0 and 1. Okay, that's a 1. Then now it's a good idea to take a voting, right? See here, these 3 persons are different. You can say this is different than this and this, right? This and this. This all are different. Here they were not different. They were all equal. So they were all same, very similar. So that's why we do this bootstrapping. Okay. Understood? Okay. Okay. Now in boosting, what happens is, one thing is add a boost. One is gradient boost. There are other boosting also there. So something like XG boost is there, but this is just an upgraded version of gradient boost. Okay, nothing like we just compute things very differently somewhat. That's all. And I guess some other boosting are also there, but don't worry. In this boosting, 2 points are there: ADA boost and gradient boost. ADA boost and say gradient, right? Gradient boost is also there. Here what we do is, in ADA boost, what we do is we only take stumps. Okay. So stump is, we take a decision here. So decision can be, let's say, x0 less than 0, something like this, okay? Less than 0.5 something, and it will give you 2 leaves. So I'm just drawing leaves as this, like rounded something, right? So these are leaves. And in ADA boost, we can only make stumps only. Okay, stumps. In this case, it's not true. Though there is a difference in how we create this decision tree here also. Okay, here decision tree can have multiple decisions, right? So like 3, something like this, right? So multiple decision trees. And here, let's say I have leaf nodes. So this leaf nodes, okay, in this case, leaf nodes can go up to, okay. I'm not saying less is not possible. I'm saying up to like 32. So generally, this is what we take. Generally, okay. Less we can take, like 2, 3, 4. 2 also we can take. 3 also we can take. 4 also we can take. But up, like usually, like most of the cases, this is like the leaf nodes will be between 8 to 32. Okay, in gradient boosting. Now in ADA boost, we take stumps, and what else is there? Okay, yeah. In this, what happens is, we have stump 1. Okay, stump 1 is there. Then the data goes to stump 2. Stump 2, and it's possible that this stump is more weighted, or I will say amount of say. Okay, I will say amount of say. So if you take both the stump 1 and stump 2, then it's possible, it's totally possible that stump 2 will have higher say in a prediction than stump 1. Okay, so this is how database, in the database we have something amount of say, something like this concept is there, or we call this as weight also, weight, right? That this have higher weightage. So weight, just everywhere weight comes, so it's confusing, but here I'm just saying that amount of say is higher, okay, for stump 2. In this case, we don't have like amount of say or anything. In this way, we have learning rate, okay. And in this ADA boost, the stump is being made with the feature that's okay. So in this we use feature, okay. We use feature to build this stump. Features to build the stumps, okay. In this case, we don't use features. We take residuals, okay. Residuals we take, and then on that we create this decision tree, okay. Because it's not going to be stump. It can go up to 8 to 32 leaves, okay. So we, in this case, we take residuals. So what is residual is, so let's say I have this dots are there, right? I want to predict it, and generally what we used to do is we make this linear regression, right? So this is residual, right? Y minus y predicted whole square is residual. Yes. Right. So we take this residuals, and then of residuals we take the decision tree. So you must be thinking why we do that. What is the important of it? So let's say my y true was, let's say, 170. I want to predict that, okay, and I have give me a minute. Let's think. Okay, so let's say I have this feature matrix, okay. Take one more. Okay. So this is going to be like this 0, x1. So these are like feature columns. This is I. So this is 170, 171, 172, 173. Okay, 170, something like this. So the first prediction I will take that what spread. Okay, when we get the new data, we want to predict something, right? So we want to make a model. How that model is going to be? So something I will say first time that it's going to be just the average, okay? Just the average. So if I take average of it, maybe it's going to be 171.5. Okay, something like so. So let me take 171. Easier for me to speak, but this is average. Okay.
So this is average of what?
Average of,
average of all the features. Okay.
Yeah, average of not feature but target. Average of this target. Okay, y mean. This is my first prediction, right? So let's say this one also 171, something like this. Okay. So let's say for this, I'm saying that my output is 171, but this is not true, right? This should update it, get updated. So to update that, what we do is we take alpha is a learning rate. Okay, learning rate. And then we have something we got out of residual tree. So what is residual tree? I will show that. Okay. Okay. Let's say problem is housing price. Okay, let's say housing price problem is there. Housing price. We have area, and what else we have? We have something. Let me take something binary. So that is easier to explain. Let's say locality. How is it like? House condition. Maybe let's say house condition. Okay, I'll say this condition. Good or bad. Okay, so good, good, bad, bad, and something like this. Okay, and area can be 246 1000 kilometers. So I will just write that this is in 1000 square meter or something, square meter square or something like that. 246. Then let's say let me take 100, 121, 242, something. And the price is, let's say in rupees, if I say, okay, in rupees, if I'm say, price is, let's say, let me take this price in maybe lakhs. Okay, lakhs. Lakhs is like 5, 10 power 5. Okay. Then maybe the price of this is maybe, let's say 30, 20, 32, and let me take something even. So let's 26. Okay, so something like this. Something like this prices are there. Okay, I'll take residual of. So first part I said is I'll take mean of it. Okay, mean, y mean. So this is mean. This is mean. This is y. Sorry, mean. I will take mean of this, and mean is going to be 30 plus 20 plus 32 plus 26 divided by 4. Which is going to be 50, 50 plus 82, 88, and 98, and 108. Okay, 108 divided by 4, which is also going to be 4 to 8, 2, 8, and 7, 4. So okay, 7 to 4 is 28. No, 7 into 4 is not 28. 6 also. Yes. Yes, yes, it's 28. Okay, so 27 is the mean. So what I'm saying is that y predicted is 27 for this, 27 for this, 27 for this, and 27 for this. Now I will take residuals. Okay, I'll take residuals. Okay. Okay, bear with me. Like this is mean, but these are residuals. So here I have minus and square, right? So we'll take always positive as a residual, because otherwise if you take plus and minus, then the total error or sum of square is not going to be positive, right? So this is 30 minus 27 is 3. 3 square is 9. In this case it's 7 square 49. In this case it's 5, and this is going to be 25. And in this case 1. 1 square is 1. Okay, so this is how I got residuals. Now in decision tree, what we used to do is we used to create a decision tree based on x and y, right, features. In this case we will build decision tree x and residuals. Nothing changed, right? So like you know how to build the decision tree, but this time we'll use as residuals, not the y itself. Okay, and how it helps is in decision tree, what we used to do is let's say this is my decision tree. It called build up. Okay, it may be build up further, something like this. So this is a decision tree. Okay, now this is built, this overfitted or something like if I let it fit all of it, If I don't constrain it, it will go and overfit my data, everything, and now it's over. Like whatever it was able to do it, like how much my score is there, I can't update or anything. Now whatever, let's say I made mistakes, right? Score is now can't change, right? Training score, you can say it's training score or something, right? I can't change it now. In this case, I can't update anything. I can't do anything. Now, whatever it built. Like there is nothing I can do with it. But in this gradient boosting, what we do is we upgrade, right? We upgrade this. We go further and further, nearer to the point. So let's say my prediction I need to make is 30, right? It predicted 27. It should predict 30. I need to go from 27 to like 30, right? This is my journey. I want to travel this. So how will I do that? So 27 plus whatever error I made. Let's say I made error of 9 I made, and if I multiply alpha something, then let's say alpha is 0.1, right? So I can go like 27.9. Okay, so then in next cycle I will go somewhere like 28 point something, then in something like, so this is how gradient boosting works. So in this case, I will just create this decision tree. Now after calculating this residuals, I'll make a decision tree for this residuals and features. So now from feature, find the residuals, and then I will take alpha and then move ahead, right? Again. Now, okay, so see, somewhere what happens is, okay, see, so this is where we started. Okay, this is x and this is y. This is y and this x. We started here, and our prediction. So this is y hat. Let's say this is y hat, right? First time I'll get y mean as my y hat. So this is first one. In second one will be it will be y mean plus alpha plus whatever from residual decision tree I made using this x and then residuals. Okay, so the residuals I got from this two I got this residuals. Okay, I'll build this from that alpha and this residuals. I will like how we do predict with decision trees. We'll do that, and alpha time I will multiply that. So I will write, let's say, residuals. Residual value. Okay, this is how my so this is my first prediction. This is my first one. This is my second one. Okay, now what will I do? I have y. This is my y pred, right? Y pred. I have this y. So I have this y also. Okay, I have this y. Again, I will compute residuals. I will compute the residuals, and the cycle repeats itself, right? So residual I have, I'll make residual tree from this. Then I will compute this one again, this part, and then I will again have predictions. Then I will again have y is already there, like, right? Again we'll do residual. Then again I will compute the residual values, like residual plot I will make. Okay, residual decision tree I will make, and then again, so it's like cycle, right? So this is how the cycle goes on, and it can go up to any level, like until it converges. Okay, so the converges, I guess, in this parameter is also there, like an iter, no change, or something like that is there. I'm not sure. Okay, we'll see this. We'll see this if it's there or not. But there is like stopping criteria is something like that. Okay, and whenever like it stop changing too much, because after some point the residual itself will be very less, right? So let's say my prediction should be like what was there, 20 30 20 32 26. So like this, 30 20 20 30 20 32 and 20 square. 32, and 26. After some point, my y pred is going to be very nearer to it, 29.99, maybe 20.123, something like this, 31.950, something. So very nearer to it. After this, if you plot residual trees and all, you'll see that there is not much changes in there. Okay, then you can that's where it will stop creating this residual plots and anything, and you will get the final model. Okay, you will get the model. So this is how gradient boosting works in ADA boost. Okay, this was all about gradient boosting. Now, if I talk about ADA boost, in ADA boost we only have stumps. First thing is we only have stumps. Okay, something like this. Only have stumps. It will go to another stump.
So stumps are the conditions. Stumps are the condition variables.
Condition variables, sorry, means?
Stumps are the conditions for creating the trees. Like x less than 5, x greater than 5, something like that.
Yeah. Oh, okay. Yeah, I understood. Okay. So in this, yes. So let me take the example again. If I have, I had area, and I had like condition of house, something, and price. Okay. So whatever it was there. Okay. So then how a stump is being made? I will take only one feature. Let's say I'm taking area. We'll take area and less than maybe some square meter, maybe 200. Okay, this is how this condition is there. Then we will compute this. This is stump. The stump is with one decision and 2 leaf nodes. This is called stump. Okay. Depth is 1. So and then see, it's possible that again area comes up. I'll come to that, why it's possible. Why it's possible that again area is going to be there. And then again, like possible that now condition comes up. Okay. This is like 3 stumps we went ahead, right? This is like 3 stumps we are now. And then we have like final decision, something like this. Before that, what we need to understand is, for that, okay, I created the stump. Then what happens? Okay, yes. First thing is how will I decide on which feature I will create the stump, first stump. Okay, or any stump, like anywhere on which feature stump will create. Stump gets the created is okay. Which feature should be which feature we should select for making stump? I guess. Okay. Okay. So on which feature we should select for what for stumps. Okay. So it's being decided based on Gini index. Other index, what other criterion you heard? So this is like criteria, right?
Gini entropy.
Entropy you can use. What else is there? Anything else? Anything else? Square error. Okay, we can do that, but Gini and R are for classification, right? This is for classification. This is also so this is like this, like In this case, no, Ginny is for both, I guess. To see. But this all thing you can use, okay? This all like how we judge a decision tree. That is, it's a good one or bad one. Same way we'll create the stumps and we'll say that which stump we should select. So let's say if Ginny is lesser for something, Ginny is higher. Like Ginny is 1 minus probability of A minus probability of B square, I guess. So this is like Ginny. Okay, so this is where we will decide how stump will get selected. Okay, so we will create stump from both of them, like area and house condition, right? House condition. So whichever was able to classify better, right? With only stumps only, it was, let's say this is better or this is better, then we'll take that as a first stump. Okay, now first stump is there. We have the first stump. Let's say let me take area. This is my first stump I have. Now there is something we need to compute is amount of say. How much this stump will have a say in the final prediction. So how we do that? So amount of say is okay. There is something called total error which we compute. So I'm taking like as a total error is, if it's a regression problem, then the total error is going to be squared error or something like this, right? But if it's a classification, then like Ginny or something like that, right? Or like misclassified point. How it? Oh yes, that feature matrix, something like. So if it's a classification problem, it's going to be something like this, like here is true positive, true negative or something, true positive, and here positive but false, negative but false, like something like this. So from this you can actually compute like how much total error was there. So okay, one thing we forget to do in Adaboost is we did created a stump, but okay, one thing we forget is, okay, so this is y, this area, and this is condition. First, what we'll do is we'll assign weights also. So this weights is also there. In Adaboost, we have something called weight. So weight is always like in first cycle, what we do is we 1 divide by number of samples. Okay, so I will just write this samples. Okay. So everybody will have similar weights in the beginning. Okay. 1 divided by number of samples, something like that. So everybody will have similar weights. Nothing. So nothing is going to change in the first stump. So first stump creation will create stump as we did it. Okay. Then okay. So this total error made by the first stump. Okay, first stump, because we are yet there only, like we are there in first stump only, is going to be will sum total, right? Sum, right? So we'll take weights. So these are weights. We'll take weight of incorrectly classified only, because we want error, right? Error and total. So incorrectly classified points, right? Points. Okay. And amount of say is going to be something like 1 by 2. See, don't worry about the formula if you don't remember it. We are not going to ask in MLP course, but just for the total error, right? Something. So this is the amount of say. We use this amount of say we have now. we have weight. So from this we got total error, and then okay, then what we do is first we had, let's say we had like 5 features. Okay, 5 samples we had. So earlier, like weight was 1 by 5, 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 something. So this is how the weights were assigned earlier. So let's say these two were incorrectly classified. Okay, then total error is going to be 1 by 5 plus 1 by 5. So it's going 2 by 5. And amount of say okay, is going to be 1 by 2 log. I will take 1 minus 2 by 5 divided by 2 by 5. Okay, I'll take this, and whatever value comes up, this is the amount of say. So let's say this comes up as maybe 0.8 comes up. Okay, it can be anything. So I'm not computing this. Okay, not calculated. I'll just write it here because. So what I need to do is I need to increase the weight of it, and I need to decrease the weight of this. So whichever correctly predicted, I need to decrease it. Okay, I need to decrease this, and I need to increase this. And it's very simple. Like how to increase weight of something is, what I will do is I'll take whatever weight was there earlier. Okay.
Sir, we increase the weight of correctly predicted.
Yes, we do that. Actually, what we do is, see, it's a how algorithm goes.
We increase the weight of incorrectly predicted, right?
Yes, incorrect only, right? These are incorrect, right? These are incorrect. See, I'm increasing for that only. These are incorrect. And this only I use for total error. I didn't use others, rest of the 3. Okay. Incorrect points.
Can you show the formula log of 1 minus total error?
Log of 1 minus total error divided by total error.
Okay.
This 1 by 2, I'll multiply by. Okay. Okay, so I have weight now.
Sir, what is the logic behind like increasing the weight of wrongly predicted or incorrect prediction?
Give me a minute.
Why do we want to increase the weight of incorrect predictions?
Okay, so see, what we wanted to increase for that is, see, that comes next. Like what we are going to do next is that will explain why we want to do that. Okay.
From MLT, sir said when you give that will get corrected, right? So you don't want your incorrect more of incorrect. So you take the incorrect and make it correct. That's what it's doing. The next tree will do that.
Yes. So yeah,
that's
correct.
The reason for taking the incorrect ones.
Yes, correct. But so how I'm going to increase it? I will take for incorrect one. What I will do is I want to increase it, right? So what I will do is I will multiply weight whatever earlier was there, e power amount of say. This is for incorrect. Okay, incorrect weights. And for correct one, just the one thing only. I'll take the weight. I'll multiply e minus of amount of say. Okay. So this is going to increase, but this is going to decrease. Okay. Now I have new weights. Now what I will do is I'll create a bucket of it. So I will show you. See. Earlier we had 1.5, 1.5, 1.5, 1.5, and 1 by 5. Now these two are incorrect. Okay, this two are incorrect. So this is going to increase. Okay, so let's say 1 by 5 is 0.2, right? 0.2, it's like 0.2. Then now let's say it becomes 0.3. Okay, so this is also 0.3, and it's possible that it can go. It should not stay in 1, 0. So currently, if you see, this is less than 1. The sum is less than 1. It's possible that the sum can go more than this or less than this also. Okay. So here I have 0.3, maybe I have 0.2, 0. No, I will reduce it, right? So let's say 0.15. Then this is also 0.15, 0.15. So if I total this up, I'll have 0.90 total. Now I will scale this up so that it will become 0 to the total will become 1. I'll scale this up. First thing I will do that. How to scale is I will divide all of this by 0.90. Okay, 0.90. If I do in this case, it's easy. So 15 by 90 is 6. 1 by 6. Correct. And this is 1 by 3. This is also 1 by 3. 1 by 6 and 1 by 6. Okay. Now see, I have this thing. Now if you see, this is 1 by 6. Now if I'll just sum it up. Okay, 1 by 6 plus 1 by 3. I'll have 1 by 6 plus 1 by 3 plus 1 by 3. And like this, 1 by 6 plus 1 by 3 plus 1 by 3. You kind of know this thing from CDF, PDF and CDF, right? In PDF we have, then we compute CDF. This is a similar thing. Okay, then 1 by 6 and total is 1. Okay, here the total is going to be 1. Now these buckets are being made. So these are values of bucket. So let me take how much is going to be. 1 by 6 is yes 0. How much? I'm not sure. Okay, I'm not sure how much is going to be. Yeah. So what I will do is I will take. Earlier I had 5 samples, right? 5 samples were there. Now I will select 5 samples. 1, 2, 3, 4, and 5 samples I will select. The selection procedure is going to happen, and I will take anything between random number, random weight, between like 0 to 1. Okay, anything can happen. Now, what is the probability that it's going to be of incorrect one? Because it's going to be higher, right? See, this bucket is 1.6 to 1.6 plus 3. It's sorry. It was supposed to be like started from 0, then 1.6, then 1.6 plus 3, and then 1.3, and then 1. Okay, something like this. Okay. And this is 0. Okay, something like this. So now see, this is one bucket. Okay, now this is another bucket. This is also another bucket, and this is another bucket. See, now what I mean by buckets is, okay, let's say if my number line is like this, okay, this is 0 and 1. If I just take 0.1, 0.2, 0.3, 0.4, and like that till 1. Okay, everything is there. If I take this number line, and then if I ask you what is the probability of getting selected something here, from this bucket. Okay, this is a bucket. This is a bucket, and this is a number line. Just don't think anything else. Just think how what is the probability of something getting selected over it and something from this bucket? Are they going to be equal or not? Probability of getting selected. Something to be selected from 0.2 to 0.3, and let's say 0.3 and 0.4. The probability of some number getting selected out of this and this is going to be equal, right? Because the range is similar. It's not different. So yes. What if one bucket is bigger than another? Like let's say this is 0 to 0.1, but this another bucket is like 0.1 to 0.5. Now, if I ask you, what is probability of getting selected from here? Okay, you'll say the probability is 0.1 out of 1, and this is 0.4 out of 1, right? Probability. So probability wise, more things can get selected from this bucket. So this is why we made these buckets. Okay, these are signify, these are telling me that these buckets are there. From that, I will take this random numbers from 0 to 1, and there is highly likely that some sample will come out from more samples will come out from the bigger buckets, and bigger buckets are where errors are larger, right? Those are going to be bigger buckets, correct? So this is, let's say this 0 to 1 by 6. This bucket is 0 to 1 by 6. This is 1 by 6 to 1 by 3. This is bigger one. This is also bigger one. And if you see this one, this is a smaller one, right? This length is 1 by 6. This length is 1 by 3. This length is 1 by 3. And this is also 1 by this is 1 by 6, right? So this is a smaller bucket than compared to this. Okay. And this is also, so these are equal buckets, but these are bigger than 1 by 6 bucket. So this way we'll select some number, will select out of this random weight, and then we'll again select some samples. So what will happen is happens that R2 got selected where error was 1 by 3. Okay, weight was 1 by 3. Okay, weight was 1 by 3. Then again let's R1 selected, then R3 selected, R3 selected, and R2 select, R2 select. Yes, so this all have 1 by 3 weight, 1 by 3 weight, 1 by 3, and this is one as 1 by 6, right? So this is how we will create a new sample. This is now like new X. This is going to be a new feature. Okay, we'll start now. For this feature we had area and all also, right? Area and condition. This we will have. So on this sample, like the new sample we have, okay, earlier sample we used something, we created stump, we did everything. Now we have new sample. So this is X, this X dash. Now we'll use same thing to do what we did here. We'll create a stump out of it, and from stump we'll able to say we'll do, yeah, in this case also we'll assign weights. Okay, first thing we assign weight. So let me write steps what we should do. Okay, so first thing is we assign weights. Okay, assign weights. Second thing is we make stump. Okay, third thing is we made stump. We will increase weight for incorrect, right? Yes, we will increase weight for incorrect classified samples. Increase weight for incorrect samples, okay, and decrease also. So this will both be like similar, like decrease also will do decrease for correct. Okay, increase weight for incorrect, decrease for correct. We did that. Then what we'll do, we'll compute total error and amount of say. Okay, I guess we should. Okay.
So do we need to calculate all these steps you have just explained for tomorrow's exam? Are we going to
So
attempt
let's
this
say some
question?
concept is there related to it. You can solve using this, right? If you know how Adabus works, that's why I'm explaining it. So I mean, see, in MLP, how can I say? So this is not MLP is application of MLT, right? And in ML, like in quizzes and all, we generally give you questions which you have to compute which you have to compute without even having the collab itself, right? That is a big task. So how would you know how to do this? So we'll not ask this much, like don't worry, but this all things are there now. See, we were able to say what is gradient boosting and all. It's just final part, don't worry. Total error amount of say we did. Then based on this, we'll increase weight and increase weights. Right. Increase weights for incorrect. Okay. Now I have this increased weight and all. I will create buckets. And then I will select new samples. Select samples. And then I have new samples. So I'll repeat this. Okay. I'll just go to here and I will repeat. So this is how the cycle goes on for ADA boost. I think I covered that part. One more part is wait. Okay, one thing is remained is stacking. What is it? Why is it different from anything else? Like how it is different from bagging or boosting is. In bagging, what we did is we created multiple models and then take voting and all. In boosting, something is predicted by model 1 or a stump or something like that. Then it goes to second one. Then it goes to third one, something like that. So the whatever the mistakes made by first one will get corrected by second one, something like this. So this is the concept behind boosting, and this is bagging. But in stacking, what we do is we take the data. So data is there. Okay. Data. Let me take X and Y. X and Y. Now we create one model. Model 1. Then we have model 2. Model 2 we also have. Now we have some output from it, like some output. Let's say it's a regression problem. Right? Let's say it gave 70 and this gave 172. Now, in this case, we'll not take the mean of it, which we usually do in bagging type. What we'll do is we'll feed this thing to another model. So this is like model 3 or final model. Okay. Model 3. This will go inside this. And what will be so this is going to be X. Okay. This is going to be X. What is going to be Y? Y is going to be this one. This Y will be from here and we'll predict it. So how this looks like is, I'm like, let's say I will take linear regression here. Linear. And another one I'll take is SVR. Okay. I took SVR. These are my row 1, row 2, row 3. Okay. It predicted value 170, 172. Okay. it got rated, let's say 159, 134, 128, 135, something like that. With this I got this features. These are now features itself. Now y I have, right, from earlier, like whatever I feed y to here or here, this y is similar y is this one. Okay, this can be anything like 174, 160, 130, something like this. Okay, this will go into another model. This model can be so a linear SVR. Let's say this model I'm taking as dysentery regressor. Okay, dysentery regressor. This both feature will go, and this is y. So how I will predict is 170, 172, and 174, right? So this is how I will predict from this one. So this is how stacking works. That's all. Like stacking is just it will take input of both earlier models and then give you output. Okay. I think I covered all in week 8 also. Now let me show something related to Ada Boost. Okay. See, we have estimator. You know, we have to give one estimator in Ada Boost, right? Okay, an estimator is how many estimator you want to build, like one after one after one. Learning rate is there in Ada Boost. Weight applied to each classifier at each visiting iteration. Okay, so with amount of say we can give this also. Yes.
So this learning rate will be separate for each record, or
For
it will be
each
common across the entire feature.
No, it will be common. It is going to be common. So we'll not have different learning rates for different ones.
Okay.
Different is going to be weights only. Okay, algorithms. So these are like algorithm. Don't worry about it. Nothing is going to come out of this. This is base estimator. So in Ada Boost, like in classical Ada Boost, which we usually study in theories and all, we use this as decision trees only, as a base or as a estimator. But sklearn supports all others also, like linear regression. You can use. So this is a classifier. Let's say you can use logistic regression. SVC you can use. You can use stochastic gradient, SGD classifier, something like that. Anything you can use in Ada Boost. Okay, there's few parameters are there. Okay, this one parameter, this feature importance is there. You can use this to get how much a feature is important. Okay, this is like kind of it is going to compute you. It is going to give you like we want to create stumps, right? It can give you which is going to be the first stump. It kind of gives away that information, this feature importance. Okay, after that it's not possible. In first iteration, whatever is going to be the stump, this can tell you. So it will tell you which important is feature with some values. Okay, you can run this thing and see which features are important. So there is something like feature selection is there, right? You can use this feature importance values from like select from model, like that feature selectors are there. Select from model, you can use this thing. Okay, other is Ada Boost. If I go to gradient boost, I go to gradient boost. In gradient boost, we have loss. That is okay. Learning rates. Learning rate is the right alpha time regression tree. In n estimators, that's fine. Subsample. Okay, in this bootstrapping, right? You can do bootstrapping with this gradient boosting also. So this can help doing that. So if you write subsample less than 1, then it will take some smaller amount of rows, right? You can okay. Criterion is fine. Minimum sample split. So like we do in decision tree, minimum sample split is we should have this much sample. So let's say if I set 5 as a minimum sample split, and my decision tree grow, and at a decision point, okay, at a decision point, as a leaf, it will become leaf only, or the further tree will not grow if I have less than minimum sample split. This amount of sample should be there to split further. Minimum sample leaf is in leaf, that many sample should be available. So by default it's 1, right? Because see, so 1 means it's going to be fully grown tree. After that, there is no decision like after. So it's like completely pure trees are there. Pure leaves you will get. Okay, not pure tree. Pure leaves you will get to have minimum sample leaf 1. Like same thing in decision tree also. Minimum fraction leaf weight is sum of total weights required to be at leaf node. Total weight and sample it is not provided. What is that? Minimum weighted fraction of the sum of total weights, which is I can. So if I sum of total of weights for all input samples, this is not present in decision tree, right? Minimum weight fraction leaf. Okay, minimum weight fraction of the sum of total weights. Leaf node samples have equal weight. Okay. I need to say this. Okay, I'm not sure about what is this, but like I can understand what's written here, but how it's going to be important, that I'm not sure. Or when it makes difference. Okay, minimum impurity decrease is like if a split happens, like so earlier, like when we start a decision tree, we have some impurity, right? So by default, when there is nothing, so first decision is made, that's where the impurity is. Out of y it will compute. Okay, out of from the labels it will compute the impurity. Then if impurity is not decreasing by this much amount, then it will not for the split. Okay. What we have max features, so we can select how much how max features are there. So on gradient boosting we have multiple trees. Okay, so if you want not all trees have access to all the data, then you can write like you can select how many max features you want. You can even give int or float. So if you give like say 3 or 4, then it will only take any 3 or any 4 features for building a decision tree. Okay, verbose is okay. Max leaf node. So how many maximum leaf nodes should be there, right? So maximum leaf node is when we have one decision, we have 2. Then if you make 2 decisions, then we have maybe 4 leaf nodes, something like this. So if you, how many leaf nodes you want maximum, you can set that also. And like here, this parameter is that, okay, I was certain. So when an iteration no change, so after each iteration, there is no change in the label, predicted labels, then this gradient boosting will stop. Okay. CCP alpha is like cost complexity pruning. Cost complex. It's called cost complex pruning. So higher the value, it will prune more. Okay, just remember this. So if you have higher value of alpha, yes, okay, I'm explaining gradient boost only. So if you have higher value of alpha, that means you want to prune. So it's like post pruning. After decision tree was made, you can see what is like so CCP alpha path also you can see. Then the higher the value of CCP alpha, that means you want to do that much post pruning. So earlier, like this all parameters were pre pruning. You set something higher, then tree itself won't grow. But post pruning is it grew, like the tree is grew. Now you want to cut the tree from the bottom. So that's where the CCP alpha helps. And in this, like we don't have any like this or parameter, like maximum leaf node or maximum depth, minimum weight, minimum sample leaf. Here we don't have any logic behind it. We can just, what we can do is we can randomly select one point, one number, nothing else we can do. But here we can, in CCP alpha, what we can do is we can draw the cost complexity path, and based on that we can select. So here some method is there. Okay. Now we have this.
Sir, you were saying something that higher the value of CCP alpha, what will
Yes.
happen?
It will prune more. So prune is cutting. It will cut more tree. So the depth will
Depth will reduce, right?
Yes, yes, depth will reduce.
Okay, thank you.
Ensemble, right? Yeah, ensemble. Then we have random forest is same as decision tree. Okay? All the parameters are same because random forest is built of all the decision trees. Staking classifier. We take this one, and okay, this two are last. We'll close after this. Voting. This is staking and this is voting. Okay. So staking, like we have multiple estimator, and then we'll give output of that to another estimator, and then we'll predict. So anything stack method, auto predict proba, decision tree, decision function predict. That's fine. Okay. Don't worry about it. You can read, basically. You can read and whatever it's there, but it's not going to, will not ask something from that. Final estimator, estimated. Okay. Like there is no such parameter I can see which I need to explain. In voting, we have something called soft voting and hard voting. Yes. So invoke the fit method. Okay. See, in this only one parameter is important, or which is new, which is voting hard or soft. So in hard, if it's a hard voting, let me search. There's one more good example. Difference between hard voting and soft voting. Okay. Not this one. That's change. Okay.
Sir?
Yes.
Sir, you have explained in the beginning the confusion matrix, that diagram one. So can you just, I got confused. Can you just tell me once again quickly for 2 minutes?
What is confusion matrix?
Yes. Actually, you shown some diagram, no? Actually, when we have the value for the, you shown some diagram, fork by fork matrix, and some colored ones.
Some colored one should be in this one.
Sir, can you just help me to understand, because I just.
Okay. I'll come to this. First, let me complete this. So after this, we'll complete the session, and I will take your question. Okay. Okay. So see, when you create this voting classifier, you can if I take this question and if I reconnect this, if I run this, we have this. Okay, see what I'm doing here. I'm just building this for this all. I am importing it, voting classifier. So this is like, so this classifier, 3 classifiers are there, and then X and Y. Okay. What else we have? So ECF1 hard voting, I'm doing it here, great. And here I'm doing soft voting. Okay, that is also great. We have see named estimated predict. Okay. This is just saying that how to let's say if I want to compute just this classifier one, which is logistic regression. So this is just an array, right? You can how to iterate the array. This is what it's actually like. You can write this ECLF1, which I created here, named estimator. Then you can .lr you can give, or this is like pandas, how we do in pandas. This is like it's saying like how to iterate or traverse, right? Traverse an array. That's all it's explaining. Don't worry about this. Now what I'm doing is I'm taking hard voting here, right? So hard voting is let's say first one output is like 1 1 and 2 2 2. Like that. Let me take 0 0 0 1 1 and 1. Okay. See, so what's happening is, let's say first classifier in voting, what happened? First classifier CLF1. Yeah, this one said the class is 0. This said class is 0, and this said class is 1. Then what we have output as 0, right? Nothing changes here. And but in soft voting, this is hard one. Okay, this is hard voting we did. In soft one, what we do is soft voting. We get probabilities. Probabilities we get. And let's say probability of it's being 0 or something, and 1, right? This probabilities will get. And let's say for classifier 1, I get 0.25. Then another is going to be 0.75. CLF2 is going to be 0.4, and this is going to be 0.6. CLF3 is going to be 0. Okay. Give me a minute. So I'm just matching with the top one, 4 and 0.5, and it's like 0.6 and or maybe that's 0.8 and 0.2. So in hard voting, what we did is we just look at the output and then voted it. That's all we did. But in soft voting, what we do is we don't directly do that. Like we sum the probabilities of it. So I'll just sum this all probabilities. Okay. So sum is like 0.75 plus 0.8, 0.75 plus 0.0.5 and 0.8. 8. Okay. And other is 0.25 plus. How come it is 0.5 only? Should be 0.6. Okay. 0.6. In this case, it's going to be 0.4 plus 0.2. Okay. In this case, see here I said something like this. Yes. So see, in this case, I directly said 0, 0. The most voted is 0. So that's why 0. But here I summed the probabilities, and here I'm getting 2.15 for class 0. So this was 0, right? The first column, and this is here 0.85, and because that one is higher than this one, that's why I'm saying it's class 0. So where does it changes when we have something like this? Okay, suppose you have probability like this. Hard voting will give you 1/3, 1 vote in favor and 2 against. So it would be 1 vote in favor and 2 against. So it will classify as negative. Okay, soft voting, average of the probabilities, which is 0.6. Okay. Okay. So let's say if I have 0.45 plus 0.45 plus 0.9, then in this case, what I have is 1.8, right? Wait, I have to take average. So okay, I can take, which is 0.6. So 0.6 is greater than 0.5, right? Greater than 0.5, which can classify as class 1. But same thing if I do this for like, so 0.5, usually how we classify is whenever we have lower than 0.5 value, we call that class 0. If you see probabilities, like here I wrote probabilities, right? So this is going to be like this only. So probability of something to happen more, 0.45, then 5.5. Right, and the other one is 0.9. So it's saying 0.9 and 1. So if you have this kind of example, then by looking at it, you'll see that the output is coming out to be something. Okay. No. Should be okay. We take average of it, and it's going to be greater than this. Then we can let me run this. Predict probability for x. For x. And this is how I got the probabilities. So we'll sum, what we'll do is we'll sum up both of them. We'll take average of both the columns, and whichever is higher, that's going to be the class. Like that is the easy another way. You can take directly take sum also. That is also okay. Okay, average is written here. You can take the sum of this, and that will also work. You can take only one side also. But in that case, you have to take average if you take one side. If you take both the sides and compare, that will also work. It's same thing. Okay. We can take mean. Or you can take mean, or what you can do is you can take a sum of both the sides, sum one, and then check this condition. This both will be similar. You can try this. This is only like important point in voting classifier. Otherwise, Latin transform and jobs is okay. Weights is okay. Okay, that's fine. Yeah. Anything else? I think we covered week 8 also. Earlier weeks are also covered. And covered. Bagging is covered, right? Oops, score out of bag. So in this thing, this bootstrap option is there, right? You can set it to false or true. So if you are bootstrapping, then only you will get this out of bag score. So out of bag is whichever not selected in bootstrapping. That's all. This is like last complete. Anything else? All new things that you all new things. No, this is not new things. This all are. I was just explaining the. Algorithm, like which is covered in MLT. This all are just parameters, right? Few parameters. Most of them are from decision tree. If you know decision tree, just prepare well for decision tree, how to build and all, what parameters are there. Then most of the problems you will be able to solve. Except this voting classifier, one thing is there, like how to vote. What is soft versus hard? Okay, final estimator. Okay, that is all.
Stacking classifier for exams?
Sorry, what?
Do we have a stacking classifier for the exam? I did not see in the lectures.
It's there in the slides. I've seen in the slides.
Okay.
Yes. Okay. So somebody was asking something related to confusion matrix. Can you repeat the question? What was it? Okay, this one in here somewhere, right? What it is? So what is this thing represent as? So see, why we have y true. Okay, when y true is what we get as a labels, right? We create labels and all. So labels can be 1 or 0, or if it's a multi-class, then 0, 1, 2, 0, 1, 2, 3, 4, 5, something like that. So if it's a binary case, we can have this. This is like out. This is like. So what I'm writing here is 0, 1, 0 is labels. How would I know that these are labels? I got this from data. I didn't. I'm creating now, but this I get. This I get from data. All right, and then something called vibrate we have, which is like also one. This 1, 0, 0, and something. Okay, it's hard to create this link. Okay. 1, 2, 1. We'll remove few of this also. Okay. 1, 0, 1, 1, 0, 1, 1. Okay. I guess this. So this I get from model prediction, right? Like you have data set like something like this, right? 124, 36, 23, 45, 34, and the output class of this is, let's say, 1. You have this kind of data, right? And then another row is there below this, right? Another row, like I think 123. Something like this. And then if this is a, you can get labels like this, right? So this is features and labels, X and Y. That's all. So this Y is here, and I will use this X to predict from my model, and I'll get this Y prediction. So from this two, I'll compute this confusion matrix. I'll plot this one, right? So while plotting this, first I'll see like how many. So this is 0, right? 0. How many I was able to find true zeros that will go here, and wherever 0 was supposed to be there, but it gave me 1. I will write here. Then wherever 0 was supposed to be, and 2 it predicted, I will write it here. Like the counts, these are all counts, nothing else. Like these are 0, 1, 2 is not classes, and it's just counts. Because currently it's like the numbers are smaller, it's looking like 0, 1, 2 only, but these are counts. And so this horizontal diagonal goes, right? This not horizontal, diagonal. The diagonal is true predicted one. So in 0, total 3 were there. Out of that 3, I was able to predict 2 correct. And in class 1, again 3 were there, and 1 out of that I was able to correctly predict. And in class 2, I had 4 samples, and out of that 4, I was able to correctly predict 2 only. So that's how this confusion matrix is being drawn. Okay. Okay. This one. Okay, anything else you have doubt?
Yeah, I have doubt in one old question paper, 2 question. Shall I share my screen? Hello?
Yeah, you can share. You can share your screen.
Okay. How to solve this question? Are you able to see my screen?
Yes, I can see that. So okay.
Understand what will be the output.
Fit is there a dot to array. So correct output of the code. Okay. Correct output of the code is so x is 0, 5, 7, 10.
Sorry.
Okay, no problem. 7, 10, 0, 0, 1, 1. Neighbor we did neighbor.
What's happening here? I'm still not getting.
Dot k neighbors graph of x, and I'll make that as an array. Though I understood what's been happening. How will I compute without? Okay, neighbors graph, because we have one.
So what I can observe out of these options are only the last option. So we need to find 3 neighbors at least. So at least out of these 4 points, 3 should be 1. But if we look at the last option, there are all these 4 arrays, and 3 of them are 1. But others, there are 2 also.
For others, there are.
Okay. So it is only from the options, no, not the real calculation.
Okay, see in this, see, because this is a n neighbor is 3. What I can say is, for each element, the other 3 are going to be their neighbor for everyone, right?
Okay.
So for everyone, the other 3 are going to be neighbor. So that's why it's being said like 1, 1, 1, then 0. So for 0,
Okay. Last one.
the last one is not a neighbor, but and for second one, let's say 5. So 0 is a neighbor. 7
Yeah,
is
that's what I understood. First 2 is easy. Even this for 7, the first 3 is neighbor, but 10 it's not. So that's why I got confused. Yeah. Just from the option. So there's no calculation, right? Not much.
no. Like not a calculation. You it's just a distance.
Okay. And just one more question. How to calculate? I'm not getting how to split this.
How to split this? Okay. Addition B is there. Then it's saying that you should have sample split 5, sample leaf 3, and okay, number of sample at node 10, it is split. It will result 4 nodes on the left and 6 in right. Okay, so minimum sample split is 5 and sample leaf is 3. Both the conditions are satisfied, so sample leaf.
It's asking for the split will not be made.
Yeah, but even among the 4, how do we say that?
Okay. Split will not be made. Okay, so you will see from this, right? So see, let's say you have minimum sample split. So let's say you reached a point, okay, and a node will have minimum samples, okay. They are lesser than 5. Let's say 4 are there. Okay, then you can't go further. In this case, the split will not. Yes.
So actually the first option, like it says the 10 node at n is equal to 10, left side will be 4 and right side will be 6.
Yes.
So it will be split one because the question says minimum sample length is 3. So it is greater than 3, so it will be splitting.
Yeah.
So the option. So similarly, the third option, like left side it goes only 2, 2 and right side it is 10.
Yes.
So it is not meeting the criteria, so it will not split. So the third option and fourth option becomes like that.
Okay.
Yes.
Yeah.
I didn't get this. Sorry. Can you please explain it again?
In the question is given minimum sample life is 3, right? CLF, you see the X train, X test, Y train, Y test. That's
Need a
pretty
minimum
there.
of 3, right?
Minimum 3, na? So minimum sample 3 means then their splitting can happen. Now, if you see the third option, node 12, it is splitting left side is 2 and right side is
This
10.
less than 3. Okay.
Yeah, so it will not meet.
Yes.
Similarly, the fourth one also it will not meet.
Yeah, if you draw the tree, if you draw the stump itself, the last stump, you'll get it. Okay, just draw how much goes in left and how much goes in right, and does it satisfy the condition which you have given? Yes or no, then you'll understand.
So sir, in this question, we can choose one of these two, like the minimum sample split and minimum samples leave,
Yes.
to decide whether it will split further or not. Is it true?
Yes.
Like one of them can be true or both has to be true?
No, only one. So what happens is whenever first condition is met, that's where it stops. Okay. So if second condition satisfies, good. If it doesn't, then also okay. So like whenever one condition is met, that's where this splitting will stop itself.
Okay. Got it.
Thank you.
Uma ma'am, I want you to share that first problem again of
Yeah.
neighbor graph. I did not understand. If you could explain me, please.
Yeah. One second.
And sir, will classifier chains come in exam?
Classifier chain. What is? I didn't understand. What is chain?
Uh, it was explained in one of the videos, classifier chains.
Which one you're asking? Kalpita?
The neighbors one.
Yeah. This one, they said in all the options, there is not three. Only in the last option, there are 3 neighbors, right? Hello?
3 neighbors as in, can you point
Like
out?
I don't have a pen. See, the problem is like finding neighbors, right? Is equal to n neighbors is equal to 3. So, and finally we are calculating a is equal to nay dot graph. So the graph should have for each point the neighbor calculation, right? So the neighbors are 3. Only in the last option it is showing the neighbors of 3. The other options there are only 2 in some of the cases.
Okay, understood.
Yeah, it is just no calculation. I was spinning
Options.
my
Okay,
head.
through options we eliminate.
Yeah, just the options. There is no calculation at all or matching the answer, nothing like that.
Understood. Thank you, ma'am.
Yeah, so mostly in MLP questions, whenever you solve, try to do option elimination. That is much easier than solving anything. Okay, don't go into solving because most of the things are like that. You can't solve it.
This question, is it sum square error? R2 square is what? They just asked the R2 square for this question.
R2 square, right?
How to do? Because it is given y true, y predict. Is it like mean squared error?
No, it's not like mean squared error. In what it's saying, calculate the coefficient information based on the code. It's not mean squared error. Wait, how to compute R2 square?
Is it R2 sum square? SSE?
You have formula for R squared in one of the lectures, 1 minus u by v.
Pardon?
In one of the lectures, you have formula for R squared, which says it is 1 minus u by v, where u is residual sum of squares and v is total sum of squares. We can use that anytime.
Yes, you can. Yes.
Okay. Thank you.
Sir, I was asking about these classifier chains.
I'm not sure. Like I've never heard of classifier chain. Maybe that is bugging.
Like after we discuss one versus rest and one versus one classifier, there was classifier like for multi-output classifiers. There was classifier chain. after sir discussed one versus rest and one versus one. In the videos, sir.
Okay, classifier chain. It's okay. Okay, it's here. Just binary classifier into chain informal expectation.
So I just wanted to understand how the prediction works in this case. Like, the output of one classifier, binary classifier, how is it
Yeah.
given to the other one, which is chained with it?
Okay. So label classification.
And what type of questions, like theoretical questions, can come from this type?
Multi output. Okay. First thing is this classifier chain is used when we have multi-class problem.
Multi-label, multi-class, multi-output.
Yes, you can say that also. So the output is not going to be 0 or it can be 0 and 1, 0 and 2, and only 1 also possible, 0 also possible. In that case, we use this classifier chain. Okay. Though see, first yes, this is not part of our curriculum, but I can explain it. What happens is, see, usually what happens is we compute one class only, right? For a given input, we compute one class, right? X and versus y we compute that's all. But here we can't stop at predicting one point because it's a multi-class. It's possible that maybe 0 we predicted, 1 is also a correct answer. So 0 and 1 should be the correct answer. So that's why this chain transformer or chain classifier is being made. Okay. So in this, what we are doing is, in this, we are chaining it. So what goes into the other one? That's what you are saying, right? There is
Yes.
no other one. There is no other one. There is only one estimator. Okay, it predicted one class. Then it goes and predicts with same feature the other class also.
So when we are saying that we chain the classifiers together, what are we
Yes.
doing then?
What we are chaining.
Is it relevant for tomorrow's quiz?
No, it's not relevant. No, it's
So
not.
then, can you explain it in your other live sessions, maybe one day, how this works?
Sure, we can do that. Because I need to see also.
Yes, please take your time, and then we can discuss in the
Okay.
coming sessions.
Okay.
Sir, I have a question if I can share my screen.
Sure.
I'm not sure if it is visible.
It's visible. Okay.
Okay, the first question.
Which question?
Ashok has to train a logistic regression model on a data set with gradient descendant approach. Which of the following solvers can be used? For logistic regression, all I understand is all 5 are there, but how do we understand for gradient descent it can be SAG or Saga only? How do we conclude that, sir?
That you have to read documentation of a scalar. In that it's written. I know that it's written there.
So this SAG stands for stochastic average gradient, something like that. Maybe because of that.
Yes.
Okay.
Yeah.
And Saga is like a more proper version, a different version of SAG.
Okay. Okay, got it. Maybe I'll go through the document as well, sir, as you said.
Yes, you can go through that.
Okay.
I have one question. Can I share my screen?
Sure.
Sir, actually, I have doubt in options. I know the definitions. Where is it?
One doubt in the previous question, logistic regression also used stochastic gradient approach.
Logistic regression.
Question is very confusing.
I mean, not that way. So in stochastic gradient descent, if you write SGD regressor, that if you use log loss.
Yeah, that is there. But in this question, it is written as in logistic regression, stochastic gradient approach. Is that there? Is something like that there?
It's not
That
there.
we saw in the sklearn. In
No,
SGD, if you use
logistic
loss as log, it will become logistic regression, right?
Yes.
But in the question is given as logistic regression, the approach is gradient. So does that happen?
No. That is not possible. Stochastic gradient descent is not there. In that, only gradient descent is there.
Yeah, because that question is very
Logistic regression.
confusing. Yeah.
Yes.
So is this means in this example, this C is a SKLN SVM means parameter, but in
Yes.
in this parameter, that C is a inversely proportional to the regulation parameter.
Correct.
So if the
Yes, I remember this question. The in this options are given which one is incorrect or correct.
yes, sir, that is
The confusion. Yeah, but your point is valid. So it's like C is inversely proportional to alpha. So when we increase the alpha, we increase the regularization. But in this case, it will decrease.
yes, sir. That so
Yes.
this option is wrong here.
Yes. Options. The given option. So which one are read are the correct.
Okay, sir. Okay, that is. Okay. Thank you, sir.
Okay.
So may I ask one more thing, please?
Yes.
So in this activity question, I don't understand why C equal to 1 is not considered.
Values may overcome the problem or okay. So see, overfitting is there, right? Now we want to regularize it. Regularization, you want to
will reduce C.
Yes, you want to reduce the C. Okay, so 10 is there, and pipeline. So which of following areas may overcome the problem of overfitting?
When I chose C school 1, it was giving a wrong answer.
Wrong answer, yeah.
1 is also a right answer. Standard scalar is okay. The increase in C, yeah, it should be correct. That's in the portal. Is this given in the portal?
Yes, sir. 7.6, question number 5.
Okay. No. 1 is also correct answer.
Okay. Yeah. Thank you.
Linear SVC.
Thank you, sir. Thank you for your patience.
Yeah. Okay, everyone. Thanks. Bye. Thanks for joining. Best of luck.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. All the best to all. Thank you.
Thank you.